In this lesson, we will look at integral as a net change. By the end of this lesson, you should be able to set up the integrals that solve net change problems in a variety of settings. Evaluate the integral analytically and with the use of a graphing calculator. We want to use integral and the area interpretation as a way to computing the net change or the total change. One example is to find the total distance traveled, and that could be represented by an integral. So first, the net change of a position function, so let S be the position function, over this time interval, so perhaps the first hour to the fourth hour. Then the definite integral from time 0 to time 1 of its derivative is equal to the antiderivative evaluated at the upper bound and the lower bound, and then we subtract them. This is the definition of the fundamental theorem of calculus. When you want to find the definite integral of a function, you find its antiderivative and you evaluate it at the lower and the upper bound, and then you subtract them. Okay, so remember, we name S to be the position function. It could also be referred to as X, so it kind of depends. Rate will always, so this is a rate because first derivative is a rate, velocity is a rate, so the first derivative of position function is the velocity function, which is a rate. Now, rate will not always be given using derivative notation. So most of the time, they won't write it as like S prime, but they might write it as like R of t, and that's a rate function. So they'll tell you, they won't make it really specific like I did here, okay? So we will often use this formula in different ways. So if you solve for S of t1 by adding S of t0 to both sides, then we would get something like this. Okay, so I added this to both sides. I solve for S of t1. So what does this stand for? It stands for the position at time 1. So the position at time 1 is equal to, this is the initial position, because time 0 is the initial position, and then this is the net change in amount, or could be the distance. Okay, the net change in the distance is represented by that. Okay, so net change as an integral of a rate. Now let's take a look at some specific examples here. The number of cars per hour passing an observation point along a highway is called the rate of traffic flow. So the rate of traffic flow is represented by the function Q. Now notice that, as I mentioned before, rate will not always be given using derivative notation. So that's one of the examples where it's a rate, but it's not being used with derivative notation, but it's the derivative of some function. Okay. Which quantity is represented by this expression? So this expression represents the total traffic flow from time t0 to time t sub 1. So whatever those two times are, but the value of this expression represents the total traffic flow from time t0 to time t of 1. Okay. The flow rate is recorded at every 15-minute intervals between time 7 a.m. to 9 a.m. Estimate the number of cars using the highway during this 2-hour period by taking the average of the left and the right endpoint approximation. So they are saying try to figure this out using the left Riemann sum approximation and the right Riemann sum approximation, and then average them, and that will give you a good estimate of the number of cars that passes by. So first I'm going to do the left endpoint approximation. left. Now here's what I want you to be able to set up. Okay, so the integral from time 7 to 9, and this is the rate. Okay, and because I'm using the left endpoint approximation, I will first determine the length of the subinterval, and so it's every 15 minutes, and every 15 minutes is 1/4 of an hour, so 1/4. And then I will be, because I'm using the left endpoint, I use all these outputs and I skip the right endpoint. So I will be using 1044 plus 1297 plus 1478 plus 1844 plus 1451 plus 1378 plus 1155 plus 802. That is the left Riemann sum approximation. I add all those up and I get a number that is 261225. So 2612.25. Okay, that's the left endpoint approximation. Notice that I left that out. Now I'm going to do the same thing, but I'm going to use the right endpoint approximation. So the approximated traffic flow from time 7 to time 9 is equal to 1/4. Now when I use the right endpoint, I leave out the left endpoint. So write down everything except for the first left endpoint, and then add all these together, and that should give us 2486.75. Now to get a good estimate of the amount of traffic flow in the past 2 hours, we're going to add these together and we're going to average them. So 2612.25 plus 2486.75, divide that by 2, and that gives us about 2,400.